Alright guys, we're going to continue on with this. So this stuff, like I told you before, is super abstract. And I need you guys to really come with questions on Monday when we talk about this, because I think these things, again, like I said, are really abstract. Now, it's okay if you're sitting here and you're thinking, oh my gosh, I'm really overwhelmed, I'm not understanding necessarily like what all of this means. That's okay. I want to give you all the pieces first before we fit the whole thing together in the big picture, okay? So trust me, and I'm going to talk about these 3 rules that govern electron configuration. And I just want you to understand or know what they are for right now. And on Monday, we're going to make this whole thing clear by writing electron configurations and using these 3 rules, okay? So all of these quantum numbers and these 3 rules that I'm about to describe, they are all related to one another, and it will make complete, perfect, crystal clear sense on Monday. So just stay with me, just follow me up until we get to Monday, and I promise you it will make so much more sense, okay? So I have 3 rules that we just said are going to govern the way that electrons will orient themselves in an atom. The first rule is something we call the Pauli exclusion principle. And the Pauli exclusion principle says each orbital, which just means sublevel, which means shape, each orbital or each shape, electron cloud, can hold 2 electrons with opposite spins. So I told you, or I mentioned, the 4th quantum number was something called spin quantum number. I told you it could be a +1/2 or it could be a -1/2. So it could be either or. In this little box, we draw something called orbital diagrams. And orbital diagrams are a way that we can represent an electron cloud without having to draw the shapes. So right now I have one box. What orbital, based on what you have here on your pictures and based on your notes, which orbital has only one shape? You should be hopefully saying the s orbital. The s orbital only has one shape. It's just spherical. So that means I'm going to draw one box to represent the s orbital. If I draw this one box because it only has one shape to represent the s orbital, I know that it can hold a maximum of 2 electrons because there are 2 columns. So let's look at the 2nd energy level, lithium and beryllium. I can have 1 electron in this box for lithium. I can have another electron in this box for beryllium. That's what Schrodinger is saying. Now, spin quantum number tells me they need to be opposite. A big reason why they need to be opposite is because they need to try to balance each other. They need to balance. If I think of this as being a +1/2 and this being a -1/2, if I add those together, I get a neutral charge. So it's neutral. That's the goal. Remember, we want things to be neutral and happy. So I'm thinking of these, they need to be opposite arrows. We're just representing the electrons in this case as an arrow. Okay? This next rule, the 2nd rule that will govern how we write electron configurations, it's something called the Aufbau principle. The Aufbau principle states that electrons fill the lowest energy orbitals first. So that means I can't jump all the way to the 6th row, or the 6th energy level, without having every single one of the rows before filled up. And that should make a little bit of sense. We need to make sure that we're putting in a little amount of energy, then we can go to a higher energy, and then a higher energy. It's just kind of going in order. So electrons, once you fill in the lowest energy levels first, and then they can move up to a higher one, fill all of those in, move to a higher one, fill all of those in, move to a higher one. Let me show you what I mean by this. So in row number 1, I'm in energy level number 1, and I have 2 elements. I have hydrogen and I have helium. So because I have hydrogen and helium and I'm in the s orbital, it makes sense that this would be 1s for hydrogen, and then helium would be 1s because it's in the 1st row, and we said that helium was that one exception where we would call it in an s orbital. Let's look at row number 2. You labeled this before as being the s sublevel, or s orbital, and if I look at 2s, I know that these first two columns are s, and it's in the second row, so this number just tells me what energy level I'm at, and then that letter just tells me what the shape is, or what orbital I'm in. So you know this is the s orbital, second row, 2s. So that should make sense. If I go over still into this row, I'm still in the second row, so I see that too. But now I'm in the p orbital, so instead of writing s, I'm going to write p. So that should make sense. So 2s, 2p. So off-bow is stating, I need to have this filled first, then I can fill this, then I can fill this, then I'm going to go to the third row, which would be the third energy level. S sublevel in row 3, so this should make sense as being 3s. If I continue down that row, now I'm in the p sublevel. Well, I'm still in the third row, so it should make sense that this is 3p. Let's move to the fourth energy level. Fourth row, so 4. 2 columns here represent s, so 4s makes sense. D sublevel, I see D here, but here's my first problem. This is 3d. For some reason, all of these transition metals in this row tend to have an energy level that's 1 less than what row they're in. So I'm in row 4, I have 4s. And if I continue and I skip the transition metals, I still have 4p. So right now, the s and the p, it doesn't matter what row I'm in, it's going to stay that row. It's going to stay that energy level. The d orbital will always be the row that you're in, n minus 1. I'm in row 4. I take 1 away, and the d sublevel will be a 3. The only reason that we write this is because that's what we see happen in nature. Why it does that, we don't know. We just know that that's how it happens, okay? That's just the phenomenon or the observation that we see. So D sublevels, the D sublevels have an energy level, D sublevels have an energy level of n minus 1. So this is in the 4th row, I take 1 away, gives me 3d. 5th row, I have 5s because the s's, the energy level just stays the same. I get to the d's, I have to take 1 away because according to this, d sublevels have an energy level of n minus 1. So if I'm in the 5th energy level, I take 1 away, drops me down to 4d. So what this means is these have a lower amount of energy than the s's and the p's do. Okay? So 4s, 3d, 4p. 5s, 4d, 5p. 6s, 5d, 6p. 7s, 6d. We have 2 more rows that we need to fill in here, and that's the f orbital. Okay? Now you know that your f orbital, this is in the 6th row, that's in the 7th row. So they're actually going to fit here in between the s and the d orbitals, okay? So you know that these 2 rows really fit in right here. Just like the d goes down 1 energy level, the f is going to do something similar, and we see actually that the f rows, the f orbital, will go down 2 energy levels. Now again, why does this happen? It's just something that we observe. It's just something that we have seen. We don't necessarily have an explanation for that. So I'm going to change this from D now because we're talking about F. So I'm going to write F sublevels have an energy level of n minus 2. So I'm in the 6th row. This is my F row, or this is my F orbital, so it's going to be 4F. So this row would be 6F, 6S, 4F, 5D, 6P. If I go to the 7th row, 7S, if I got to go down here to my F orbital, I'm going to take 2 away. So that'd be 5F, go back up here, 6D. Okay? That is my second rule that governs electron configurations. I have one more rule, guys, and that's Hund's rule. Hund's rule can also be called the empty bus seat rule. One second, guys. Okay. Hund's rule can also be called the empty bus seat rule. And all this means is each orbital must receive an electron before it starts pairing up. So for example, I have 3 boxes drawn here. There are 3 boxes that are drawn. Which orbital do I know, which orbital do I see on my paper here that has 3 shapes? Is it the S, is it the P, is it the D, or is it the F? Which orbital, which sublevel on here has 3 shapes? You should be saying P. P has 3 shapes. So because P has 3 different shapes, or 3 different orbitals, I'm going to draw a box for each one. So let's draw a box. So 3 shapes means 3 boxes. This thing that we're doing is called orbital diagramming. Okay, we're going to do plenty of it on Monday in class together. Now, Hund's rule says that within each shape, within each sublevel, I can't pair electrons up first. One electron has to go in one box before I can start pairing. So like the empty bus seat rule. I can't have an empty bus seat. I need to make sure that I have all of you children spread out, so I have at least 1 kid in each bus seat before I start pairing. That's what this means. So for example, let's say we are in the 2nd row. Say we're in the 2nd row in the p orbital. So that means I would be starting here at boron, because the 2nd row, so it's energy level 2, p level would be those 6 columns, 3A through 8A. So let's start at boron. If I wanted to draw an electron for boron, I draw a little arrow. Let's say I want to do carbon. That's 2 in, that's 2 columns into that row, so I would do a 2nd arrow. Okay, now I want to go to nitrogen. That would be a 3rd arrow. Just means I have to give 1 arrow, 1 electron to each box, to each orbital or each shape before they start pairing up. So now, let's say we're going to go to oxygen. I'm going to draw a little electron going down. Now I can start pairing. Doesn't matter where you start pairing. No, doesn't matter at all. As long as each one has an electron first, then you can start pairing, and it doesn't matter where. So if we were at oxygen, I drew that one. Why do those have to have opposite shape, or opposite directions? Because there was a rule before, the Pauli exclusion principle, that says each shape can only hold 2 electrons. This is one shape. It holds 2 arrows, or 2 electrons. They have to be opposite spins. That's what the Pauli exclusion principle states. So now if I want to draw one for fluorine, I'm going to add in another down arrow. And if I wanted to draw neon, all of these would be full. And let's think about this, because you've been drawing Bohr models. There is a reason why I have you draw these Bohr models all the time. Neon has a full shell. It has all valence electrons. It has all of the valence electrons on the outer ring. So it is full, it is stable, it is happy. Every single one of these boxes, these 3 boxes, are filled with a maximum number of electrons. So this is just another way that we can show how or where a certain element is placed on the periodic table. Okay? Guys, this is where I want to stop right now. We are going to practice writing electron configurations based on these rules on Monday. So I'm sure you have questions on this. Again, like I said, it's super abstract, but stick with me until Monday, and promise we will have all of this cleared up, because this will really be one of the easiest things I think that you will do in this class. You will love them. They're super easy. That means we can play electron configuration battleship possibly on Monday, okay? So be ready to eat Skittles and play battleship and do electron configurations on Monday. Bye guys, have a good weekend.